So, hi again. I'm back. So what I wanted to kind of talk about was kind of the methodology that we use every day for doing some of our big data analytics. And I think this might be of interest to some of you, particularly the computer scientists. If anybody is developing your own computer, your software libraries to do data analytics, image processing sort of work, this might be something that's very interesting for you. We developed this thing called LONI Pipeline, and I wanted to kind of showcase what it's about for you. So as we kind of discussed, right, data is getting very, very big. We're getting lots of data from a number of different sources. Just in terms of neuroimaging and genetic brain data alone, this is for the math geeks in the room. These are some wavelet coefficients flying around in space. But as you are looking at all the different sources of data that we get in biomedicine, not only are we getting the neuroimaging data, we're also increasingly interested in genetics data. Genetics data was, at least up until neuroimaging started to really catch up with it, it was always put out as the big example of big data. But there's all sorts of other unformatted kind of ASCII text, metadata, phenomics data that go along with it. And so this presents a lot of computational challenges. Being able to take all this data, harvest it, place it someplace, and be able to interact with it with the potentially thousands of different software tools that are out there for dealing with it. This is something that is an active and ongoing research interest. There's also millions of dispersed hardware devices that you want to make sure that all these things work on. I was just telling Alonso that I walk around carrying, I've got a phone, I've got my laptop, 2 iPads, and that's just with me here today. And I'm sure that all of you are doing something similar with having multiple devices. And you'd like to be able to utilize all of those in one way or another to help you analyze some of your data. This gives rise to this notion of this interactome, this integration of information, of skills, of tools and technologies from across multiple disciplines. Biomedical mathematics, engineering, pure mathematics, computer science, and neuroimaging. And there's all these little push-pulls that occur across all of these boundaries about needs for processing, desires for processing, challenges where you need to be able to do it, and how do you do it efficiently across all these different applications, neuroimaging, genetics, etc. A few years ago, my colleague Arthur Toga and I went and we just looked at, in the case of neuroimaging, we went and just tried to calculate what the average size of fMRI study was in the literature. So we went and we looked in the journal Neuroimage. So are all of you familiar with that journal? It's kind of one of the big journals for neuroimaging. And we just went back to when they started the journal and we calculated what was the average size, the amount of data that was collected. And sure enough, per subject, you ended up seeing this, whoops, excuse me, wrong button. There we go. You end up seeing this exponential growth. So it has a doubling rate of about every 2 years or so about every 20 to 24 months. Not surprising because it's just Moore's law in action, right? Neuroimaging is no different. So what's interesting is that if you wait a few more years, you'll end up with twice the amount of big data that you thought was big at the time you collected it. The implication here is really interesting. Big data is data that you haven't collected yet. Think about that. In 2 years, you'll just collect twice as much more. In 4 years, it'll be twice as much more again. So really kind of interesting. So we had recognized a number of years ago, along with a bunch of others, but our group in particular, that a lot of what happens with all of this neuroimaging data that we collect is that we take a particular brain image and it becomes the input to some sort of a software tool. We're going to do, I don't know, image segmentation. So we would route the data into an image segmentation routine, and the output from that, my segmented label map of the brain, would become the input for some other step. We're going to go and measure cortical thickness. We're going to measure the volume of that particular structure. And then those statistics or numbers would become the input for something else. And you can imagine having these kind of daisy-chained sort of operations where they're input-output kind of relationships, and usually there's several parameters associated with them, various flags and options, and you can conditionalize the routines and whatnot. You're probably all familiar with how these things kind of work. neuroimaging is always this sort of thing. Ever since I was writing like bash scripts back a long time ago, it's always the same thing. And whether you're using MATLAB or Python or Perl or whatever you're doing now, it's pretty much always the same kind of a deal. But ordinarily, in any particular laboratory for neuroimaging, it's usually that the knowledge of how you do this isn't widely known, at least in neuroimaging labs. And usually there is one guy, he is El Hombre, that you go to, and he's the guru. He or she knows all the magic about how you write the code, about how you write the MATLAB, the Python, or the C++. And you, as the graduate student, would go to the almighty, all-knowing El Hombre, and you would go and you'd say, please, can you help me with my code? And they would say, go away. I don't have time for you. And they'd be very grumpy and angry with you. And so we thought that this was kind of unfortunate, right? There shouldn't just be one person who is the holder of all the knowledge. It should be something which is more equitable and more available to people. And also, because there's more, if you have more than one person, you also have an opportunity to explore the variability. If there's always one person who thinks they know everything and it's their way or the highway, it kind of defeats the purpose of exploring new methodologies which might be more efficient, which might be faster, which might be more interesting, and that you could look at the variability in how data is processed and be able to explore that as a research topic. So once again, here's this kind of picture of a workflow. It's just the kind of thing, once again, to reiterate that data goes through a number of different steps before you see it in Science magazine or Nature or wherever, or Neuroimage. You will go through a number of these different steps. And very often these steps are not well described. One of the main criticisms, I'll touch on this again in a second, is that a lot of the steps that go into how your data are processed do not get described very well, if at all, in the peer-reviewed literature. So you look at a paper, I'm pretty familiar with instances of this, where somebody would say, in their method section, we used SPM, period. And that was it. That was all they said about how they processed their data. And you guys must know this, right? There's all these parameters. If you're familiar with SPM, right, you know that there's the thresholds, the p-values. Is it family-wise error corrected? Is it, all the different ways you can correct your probabilities? How did you smooth your data, et cetera, et cetera? All that's lost, right? It's not saved anywhere. So how you got from this place to this place is sort of a mystery. And so you'd like to be able to encapsulate that. So once again, these articles don't publish all the details. But if you had that information, you could compare and contrast them. You could change one parameter and watch what the effect was very easily. You could also increasingly not just use FSL or FreeSurfer or SPM. You could cherry pick the best algorithms, the best routines out of all of them and create a big Franken workflow where it's the best of each one of those. Oh, that's a doorbell. I thought it was feedback. The best of all of those to create something that was really unique, really interesting, and specific to your particular types of data. And also, many neuroimagers, they're not really interested in being computer programmers. No offense to any people who write code in the room, but a lot of the neuroscientists, people who are the applied neuroscientist, neuroimager types, they're interested in getting neuroimaging results. They want to know, how is this brain connected? How is it different than how this brain is connected in these patients versus these patients? They're not concerned with the details of, that you used MATLAB and you use C++ and I used this particular software library. They're not computer programmers, and that stuff is lost on them. But they probably should know something about how the data was processed, what that processing pipeline was, so that they can describe it to others. And likewise, you need to kind of know how the data flows. So anyway, we saw this as a huge opportunity to develop kind of a new platform that people could use to produce workflows very easily, graphically, and be able to process their big data. So we created this thing called LONI Pipeline, and I mentioned it in my previous talk, and I'll go into a lot more detail here. So you can find information out about this at pipeline.loni, which stands for Laboratory of Neuroimaging, at USC, University of Southern California.edu. And this program is now in its 6.2 revision. We're very excited about it. We've put a lot of energy and manpower into it to be able to make it aesthetically nice to look at and to work really well. And so I want to describe this for you. So LONI Pipeline is this graphical interface. I'll just kind of skip through all that and get to this. Graphical interface, which allows you to kind of graphically construct workflows of how you process your data. And it looks just like this, and I'll show you an example. It allows you to design, to validate, to execute, and submit your large-scale processing to large-scale compute clusters. It has a number of things about tool discovery, so you can index these things. You can search for tools that have particular attributes for operations you'd like to perform. These things are, there's interoperability tricks which are built in, so you can actually have tools that, say, from FSL work nicely in the same workflow with FreeSurfer, with AFNI, with anything else that you're developing as well, so that you can create these very fantastic heterogeneous workflows that do really interesting stuff with your data. We take full advantage of distributing computers, so it's a client-server model. I'll describe a little bit more about that in a bit. So you have a client-side thing which resides on your device. You create your workflow, but when you say submit, you're connected to a cluster somewhere else, and all the processing goes on there. This is beautiful because what it means is that you're now not chained to your computer waiting for it to crunch through all of your data. You've actually shoved the job off onto a dedicated compute cluster. I showed you a picture, I think, in my last talk of what that looked like. And so the way the interface looks is just like this, where you have a kind of a canvas where you can create these workflows. And then we've gone and we've pre-built a number of what we call modules. And those modules are all they're like XML wrappers wrapped around individual functions, executables, that are all command line executables from FSL, FreeSurfer, AFNI, many of the packages that you may be familiar with. And it's also very easy to create modules around your own software library. So if you're building a set of tools to do processing of various forms, you can create them as modules and then link them together, much like we can do here, where you have these little gray disks which represent what the data is. So in here would be, say, an input image volume. So a structural MRI, a fMRI time course or something. And then this module is going to be some sort of computational operation which is going to be performed on it. So we go and we wire that together, and then we have an output which goes to, this is basically where the result is going to go. So it's basically a file path and into a directory or the name of a file. And this is a very simple workflow. And you can get kind of creative because there's FSL, AFNI, FreeSurfer, AIR, Diffusion Toolkit, Brain Suite, SPM8, a number of different tools, not only for neuroimaging, but also for genetics. So if you're doing anything with sequence alignment, with various Plink file operations, if you're familiar with the Plink file format with genetic data, you could do, there's all sorts of workflows which deal with that. We've pre-built a number of workflows as well as these individual tools, and we have them here, and anytime there's an update or a new one, whenever you connect to the server, the library automatically updates with all the newest versions. So you're always current, you're always up to date, and you're always able to stay up with the literature. And again, it's 6.2. This changes so frequently. It's kind of crazy. But there are logical, conditional things that you can set up. So you can say, if this has happened already, skip that step and do something else. You can get very creative, and you can develop things which are pretty sophisticated with multiple inputs, multiple processing steps, all linked together, wired together to do something useful. And I show you this example, not this one. Here's just another example of a more complex workflow, but it's this one. This one is like about as complicated as they come in LONI Pipeline, which is, this one is attempting to do an end-to-end processing of structural MRI, DTI, fMRI, co-register it, fit it to an atlas, put it all in one space, make sure it's all pointed the right way around, and spit out the answer in a structure that allows me to interoperate between all of those different things, those different spatial and temporal scales with that data. And so you can get pretty crafty with how complex these things can become. One of the things which is kind of cool about this is that the interface is active. It's an active, visually interesting thing. And I'll try and show you an example of this, sort of what the interface looks like here in a second. I can't get a good internet connection. My apologies, otherwise I'd show it to you in action. But when you've created a workflow and you've initiated it, and it's running, it has a number of different states. So when it's in the module that's being run in that moment, you'll see a little segmented circle spinning around that particular module. It's going around and around and around. When it finishes, that module is now completed, you get a green segmented circle, kind of a fully featured green segmented circle here. If for whatever reason there was the algorithm or the piece of software that was behind it failed, or segmentation fault, or there was some sort of a problem, it goes into an error state and it identifies it as a red segmented circle. This means that visually you can see exactly where there might have been a problem, where you may need to go and refine your code, or where you were trying to submit kind of some data to a module that couldn't accept it. So that's very nice. Another thing, there's some built-in tools to be able to go and very simply view the results. So you can do this dynamically and interactively from within the workflow. You can also download that data to your own workstation, to your laptop, or wherever. And that's also kind of nice. So as I mentioned, it's a client-server model where we have this library of different tools that we've set up. And it's easy to integrate any module that you might have written yourself. So once again, if you're writing a piece of software, say you're writing something in C++, and you're going to compile it so it runs on the command line with, say, -i, image input, the input image, -o, the output image you're going to do, and a number of other parameters, you can very easily create modules and create your own LONI Pipeline set of modules and workflows that you can then manage, maintain, and share with others as well. It's very easy to do that. You can even do some of it by dragging and dropping. You can search for and tag and search for and have feature suggestion. So we're doing something that's sort of like Amazon. Like when you buy a book, or you buy something and it says, oh, well, people who bought this book also bought this. We're doing things where we're building in that sort of a logic. So people who registered their data using this step, the next step they did was to fit it to the M&I Atlas using a tool like this. And so as people use it, we're gathering statistics about what the usage patterns are so we can make logical suggestions. So even if you've never seen neuroimaging data before in your life, but your lab director says, you need to register these data in some way, process these data, you could, with a very little minimum input, get started creating very sophisticated workflows that do exactly that. A number of different tools, again, that we have available that we've built them for. Now, one of the things which is kind of interesting is that when you're connected to the cluster, so we have a cluster at University of Southern California. We have a 3,000 node, it's like 3,500 node cluster supercomputer. It's largely dedicated to handling LONI Pipeline jobs. So I'm on my laptop, I'm creating a workflow, I'm using all these tools from all these different packages. I wire this thing up, and I've got my data sitting out on that server, and then I hit the little green button at the bottom of the interface, and it submits my job. I can keep track of the overall traffic or activity on that particular server by looking at this little speedometer here on the right side. This tells me everything about the server usage, and also my quota. And so my quota, at least when I took this little screen snapshot, was I had 549 processors available to me. So that means I can put in and use the same workflow on up to 549 different jobs. And because it's all parallelized, it means that I can finish all 549 in the same time it takes me to do one. So imagine the savings that you get there. So if I'm running FreeSurfer, right? How many of you run FreeSurfer, right? It takes like 3 days to run. Well, it may still take 3 days, but I'm able to do, in this case, 549 cases in the same amount of time. This expedites and speeds up my ability to process data very efficiently. Very, very handy. Also, depending on where you store your data, whether it's on a server, a shared resource that you have here at CIMAT, or whether it's something that is in your laboratory, or whether it's out on the cloud, you can use LONI Pipeline to access that data and pull it down and process it. Now, this is very advantageous if you're part of a multi-site collaborative where you've got investigators at UNAM, you've got investigators here, you've got Mexico City, you've got elsewhere around the country. You can put data in a centralized location, and as long as it's available, you in principle could use LONI Pipeline to get access to it. So we have a number of different cloud resource models that we're compatible with. If you're using any of the Amazon web services, Dropbox, OneDrive from Microsoft, Google Drive, and a number of others, you can use those as ways to connect, to get access to data, pull it down, and begin processing it. Pretty slick. Now, I mentioned before in one point of the talk or another that a lot of the methodologies of the workflow itself are not well described in the research papers. Somebody said I used SPM 8 and that was all they described. Well, part of us as scientists is telling other people what we do. How did we process this data? It's just saying you used SPM 8 is probably not sufficient as a description of how you treated your data. So the notion of how you treated your data and the steps in that process is referred to as its provenance. The provenance of how that data were treated. And pipeline itself, that workflow, just the file and that graph that describes what was done, that in itself is a great step towards having provenance because it describes how data flowed through a number of different steps to produce an output. And so clearly you want to be able to describe that, but we also have kind of a more advanced mode of provenance, which it keeps track of the operating system that you were using, the version of all the software that was used, even the precision of the machine and the chipset information of the processors that you're using. Because we found that if you're using an IBM computer, or you're using a Dell computer, or you're using an HP computer, you can have significant digits of precision changes between them. And that can change something, right? That might move your thing that was significant at P.01 to something which is now just a trend. You want to be careful of that. So being able to record that kind of stuff is very important. Being able to record execution times, locations, inputs, outputs, all that stuff, it's all part of provenance. And all this can get shared or stored and then shared with, say, the journals as a part of supplementary information. So you could share the workflow, you could share all the provenance information. It's extra information, so anybody reading your published article would have all the same information that you have. We're also exploring the ability to create Dockers. So you're probably familiar with some of that, where you're making these little mini virtual machines that basically do all of that. Store all of this information so you could share that Docker with other people. They'd be able to run not only your data, but also be able to pipe their own data in it, and it would run exactly as if it had been run on the original operating system. And so pretty clever ways to move forward. Now, I mentioned that there's a server side to all of this. The server side portion is very important, and we made a big effort to make sure that the server side stuff is easy and it provides the functionality that your IT managers would need in order to monitor, to manage, maintain, and take care of a cluster which is running LONI Pipeline. So you can, there's a pipeline server-side installation program, and you can go and it will help you do things like, it will help you to install SPM. It'll help you to install FreeSurfer, FSL, all these different neuroimaging tools. And if you don't have them, if you have them, it will go and search for them until it finds them through your operating system and then link to it. If you don't have them, it'll help you to download it and get it installed on your system. And you have full flexibility to be able to turn these things on and off. about which ones you need. And and I've been able to do this, and I'm not very smart. So somebody who's an IT manager should be able to do this pretty easily and go and install a pipeline. And it's very easy to go and configure. It has advanced options and whatnot, and to use this as the interface to start, manage, and maintain things. Again, here's our compute cluster that we've used. This is a lot of Hewlett-Packard hardware. We kind of went a different way. You know how usually, I haven't seen your compute cluster yet, but you know how usually the compute clusters are always put like down in the basement where no one goes because they're ugly and loud and no one really wants to look at them. We went the other direction. We, at least in this installation, we brought them up. They're on the main floor. We put these you know those kind of LED lights that are kind of in a rope? We put those inside of the cabinets, and we actually have it connected to a Lutron system that would allow you to plug it. You can even plug in your iPhone and play music through it, and the lights will pump. It'll be like a club. So you could actually do that. It's really kind of cool. And when you're submitting your LONI Pipeline jobs, this server, as one example, is running the LONI Pipeline server. It catches your jobs, it manages them, it executes them, and so all the operations, all the data, all the computation are going on here, not on my local machine. And we're actually developing, and very shortly this will be available, the technology so that at the moment it's a client-server model where the client needs to run on your Windows or your Mac or your Linux box. But we're also making it so it will run through a web browser. And so in principle, you'll be able to be standing in line at the supermarket. You can whip out your phone and you can submit LONI Pipeline jobs while you're waiting to check out with your groceries using large-scale clusters like this. So here's some more about the management and configuration. You can do all sorts of stuff with managing and configuring your cluster. You can also do things. It keeps track of what jobs are running, what libraries are being utilized, what software is running. So you can go and find out, okay, I've got a number of different AFNI jobs going on. I've got some Brain Suite, FreeSurfer, who's running them, etc. All that stuff can be managed, maintained, as well as users as well. So you can go in and see what users are running what jobs, how much resources they're using. You can change how much resources they're able to use. And IT managers always want to be able to kill people off if they don't like what they're doing. You can go in and you can stop their jobs, and so you have full control. So this is a pretty big end-to-end system for dealing with a lot of the different data challenges that we have. Just to give you a couple of examples of this in action, we've done a number of different neuroimaging applications. They're countless. And one of the things which is kind of interesting about this is, I'm just going to show you a couple of examples, but there have been literally hundreds of peer-reviewed research articles that our group has published that have utilized LONI Pipeline. We use this every day. It's become our go-to workhorse for doing large-scale processing. And anytime we have some sort of a need to develop some sort of little widget, little tool to go and take data, very often we write it. We can use MATLAB and compile it so it's command line executable, wrap a module around it, and bring it in and put it into action within a matter of minutes. And so here's an example of one of those many hundred of peer-reviewed articles. This one came out about 2012 or so, where we used some structural T1 data. We're very interested in irritable bowel syndrome. There's a lot of interest in people who have kind of lower abdominal, lower gut dysfunctions and disorders, and whether or not the presence of those disorders changes brain morphometry and connectivity. So this is an example of looking at brain morphometry where we took T1 data, we fit surfaces to it, ran it through this workflow to parcellate it, and then we made a number of different measurements on it, including the geometry of the curvature of the particular structure. And at least in this case, we found differences between patients who are normal control or who have irritable bowel syndrome or abdominal, kind of chronic abdominal pain. And so we found differences in the left cuneus, right angular gyrus, as well as different views of, these are various portions of these guys. This guy's, what the heck is that? I think this is part of the angular gyrus and whatnot, showing statistical differences between the shape characteristics, the morphometry of these particular subjects in these particular regions, which is kind of interesting because in areas of the angular gyrus is areas of where there are pain and portions of the body representing the lower abdomen are represented. And so it kind of made total sense that there might be some structural changes going on in those levels. Another thing that we've done is a lot of the combination of structural neuroimaging analysis combined with genetic analysis. So combining Alzheimer's disease neuroimaging with genetics to do genome-wide association and phenotypical, genotypical relationships. So looking at, these are a difference, kind of global difference between people who have early onset mild cognitive impairment. Again, mild cognitive impairment it's not full-on Alzheimer's, but it's where people are really, you're starting to see them struggle with their cognition, with memory, with various simple things that we probably take for granted but become kind of a struggle for those folks, versus people who are also early onset, but early onset for Alzheimer's disease. So these are people they've really have the full clinical manifestation. And in looking at areas of the amygdala and characterizing shape differences in terms of the amygdala and portions of the inferior temporal lobe. Here we can create p-value maps. These can be combined with 15 different SNP imaging interactions, obtaining these kind of 15 different biomarkers. You can also use the circular representation to kind of characterize that as well. Here's your kind of very classic Manhattan plot, and you can identify that there are about 20 significant SNPs which seem to be related to these kind of cortical differences from without these gene-SNP interactions or gene-brain interactions. And so we've been able to do stuff like that. All of that stuff that I showed you about Phineas Gage with calculating the trajectory of this iron rod that went through his head, all of the pooling of the data to smash it into, to fit this anatomical data, to fit it inside of the head of that skull, to fit the DTI data in there, to do all those calculations. All of that used a family of LONI Pipeline workflows to be able to process the data in various stages. And we assembled all that and put all that together. Now, and that's just several examples. There are literally hundreds of examples where this has been done. Now, a couple other things is that LONI Pipeline is there are many of these workflow tools. Many of you may be familiar with some of these other ones like Taverna, Kepler, Galaxy is another one. But ours is kind of special, I think. It's really unique. It's kind of graphically driven. We put a lot of effort into that. It doesn't require that your data are local. You can keep those data somewhere else. And as we're kind of talking amongst with some folks earlier, with some of these big data challenges, what's one of the big problems? It's moving that big data around. As it gets to, terabytes worth of data, it's very costly to then move it from here to there. So it may be more advantageous to take your processing to the data. And this is where LONI Pipeline can come in. You don't have to recompile anything. There's asynchronous task management. It's platform independent, so it works across all your different operating systems. And very soon it'll be able to work from within a web browser. It's a client-server model and it's grid-enabled. Now, while we have focused on neuroscience, LONI Pipeline is actually data type agnostic. If you're doing weather modeling, for example, in principle, if you have tools that deal with that, you can use LONI Pipeline to process any type of data, whether financial data, if you were so interested. Some of these other tools do not do that stuff or are just very, very specific to the type of data that they will work with. So a few of our users, so we have found that a lot of people are interested in this very thing, being able to graphically, very quickly pull together workflows, leverage workflows that are already in existence, and put these things into practice. And so here are just a family of different centers from around the world and around the world that are using LONI Pipeline. And we're very excited about seeing other people use it. Again, I visited Querétaro not long ago and had a very nice conversation with people down there who are building their computing facility. I think it'd be very exciting to see this running there. Likewise here at CIMAT would be very exciting, and then we can add your icon to the list here. So really that's about it I have for discussions of LONI Pipeline. Now, I don't develop it. I'm not that smart. We have a team of people who really are, including Petros Petrosian, Zhizhong Liu, Sam Hobel, and Ivo Dinov, who's now, used to be with us, but is now at the University of Michigan. And they're really the ones who have pulled this together to make this kind of what it is and as powerful as it is. Again, we use this every day, and it's become kind of this thing that we're very excited about because we use it so much, and it's been so productive for us. We think it might be productive for you guys, and as you're developing the tools for image processing, for registration, probabilistic modeling, tractography, diffusion tensor, spherical harmonics, all the clever math that you guys are doing and turning it into code, this might be a way for you to really productize your libraries into something you can share, you can disseminate, that you can include in peer-reviewed publications and whatnot. And so with that, thank you very much once again. And if you have any questions about LONI Pipeline or how we've used it, please let me know. We have some time left for questions. Thank you.